The year 1957 was an increasingly active one for the F-102 flight test program. Production of the F-102A during 1957 reached its highest peak since manufacturing of the F-102s was begun. Many test programs were completed during the year, and the aircraft used were returned to active tactical squadron operation. During the period of 18 January 1957 through 11 March 1957 at Holloman Air Development Center, Convair flight test personnel conducted aerial firings from the F-102A number 1793 on 2.75-inch rockets to investigate their separation from the aircraft and to demonstrate performance of the airplane as a rocket launching platform to design limits of the Dash 10 series airplanes. The firing of the 24 rocket salvos was conducted throughout the speed and altitude range of the F-102A with various combinations of live and inert head rocket loadings. Different camera angles of the same firing indicate rocket separation and stability of the platform. No unsatisfactory flight characteristics or adverse engine responses were noted as a result of the rocket firing. Flash head rockets were fired on some flights, bursting at approximately 1,500 feet, the tactical range of the rocket. The flash heads provided engineering data on rocket ballistics characteristics. The complete stability of the aircraft during firing was indicated as each test progressed. Salvos of 24 rockets each were successfully fired at altitudes ranging from 5,700 feet to 53,500 feet at speeds of Mach 0.27 to Mach 1.44. The 20 test flights and firings conducted on the 2.75 rockets showed that rocket separation from the aircraft was satisfactory for all flight conditions tested. In January 1957, at Edwards Flight Test Center, California, TF-102A emergency ejection tests were being completed. The objective of the tests was to develop a system capable of providing the pilot with a safe ejection throughout the speed and altitude range of the airplane. The problems of emergency escape from tactical airplanes have multiplied as the operational speeds and altitudes of aircraft have increased, and the escape system represents the pilot's only possibility of emergency egress from his aircraft. The use of the TF-102A cab was an advantage because it allowed the ejection of two comparable seats within 0.12 seconds of each other, the right seat using the rescue unit and the left seat the M3 catapult. The rescue unit differs from the standard cartridge M3 catapult in that the rescue-actuated catapult has incorporated a solid fuel rocket motor within the catapult inner tube. At the point of separation of the catapult tube, a continuous thrust is exerted by the rocket motor for a time interval of 0.12 to 0.28 seconds during ejection. Like the M3 catapult, the rocket and attached seat move up on a fixed rail. However, here is where the resemblance ends. Supersonic ejection in present-day equipment presents several problems. The pilot may encounter as much as 7 tons wind blast utilizing the M3 ejection catapult. This results in sharp deceleration at up to 40 Gs. To counteract these severe forces, the rocket catapult will provide seat and pilot with 5,000 pounds of upward thrust. This catapult gives a forward thrust of 4,500 pounds. Depending on speed, tests show the jolt has been decreased from 10 to 25%. During actual ejection, the seat will be automatically activated following canopy jettisoning. In the rocket tube's lower chamber, a quarter-pound charge is ignited. This pushes rocket and seat up the rail. During the last 8 inches of seat travel, the solid rocket fuel is automatically ignited. During ejection, there is a small amount of oscillation in pitch attitude and some yaw. However, the seat is much more stable during the first quarter second of ejection, when stability is needed most. The present M3 ejection catapult does little to overcome wind blast. The unbalanced seat tumbles severely, producing pilot nausea. High rotational velocities during tumbling could result in internal damage to the pilot. In review, supersonic ejection utilizing the M3 catapult often results in unsafe deceleration, extreme seat gyration, and at low speed, low altitude is not always sufficient to permit full chute deployment. The rocket ejection catapult will take a seat and pilot higher. The forward component thrust will soften the rearward jolt. Low-level ejections will also be more successful. It increases fin clearance from 30 to 44%, depending on speed of the aircraft. This was the high-speed run at Mach 0.95, during which the rocket catapults broke free from the seats. This was rectified by redesign of the seat catapult attachment points. This run showed the rocket seat attained a 15-foot higher trajectory over the tail than the M3 catapult seat. There were 8 runs made during the test period at speeds of Mach 0.30 to Mach 0.95. The objective of the rocket ejection seat catapult was to provide a more constant final ejection velocity than the standard M3 catapult throughout a varied speed range, but without increased maximum acceleration, and to reduce to a tolerable rate the jolt or aft deceleration of the pilot seat combination when it is ejected at a very high speed. Another goal was to develop a system that would make ground-level escape possible. Evaluation of tests indicated that the rescue unit decreased jolt approximately 10 to 25% and provided more time for the complete and safe deployment of the parachute. Test results were excellent, and the data obtained was to be phased into further improvements on supersonic ejection systems. During the year of 1957, at Convair, Fort Worth, approximately 46 F-102 test-assigned aircraft underwent modifications to restore them to full tactical squadron operation. With flight test assignments completed, the F-102s were flown to Fort Worth for conversion. The program was a joint operation of the contractors' Fort Worth and San Diego plants, supported by the San Antonio Air Materiel area. As each aircraft arrived, task teams made initial evaluations of the aircraft's history and to inspect and repair as necessary. After defueling, fluid removal, and protective processing, work began on big tail, buzz fix modification, and larger speed brakes. The radome and fire control systems were removed for replacement with new models. Other modifications included external fuel tank fittings, liquid oxygen system, manual unlocking canopy system, combustion starter, and rocket door improvements. When the scheduled modifications had been completed, they were checked and tested to specification tolerances. After systems check with aircraft power, the airplane was pre-flighted for contractors' mechanical and MG-10 system test flights. Air Force acceptance flights certify that the aircraft meets the tactical requirements and is ready for delivery. The conversion was now complete. Latest modifications, complete IRAN inspection, and tactical configuration have been given to the F-102A. After all inspections and acceptance flights, the F-102As were delivered to the Air Force for squadron operational assignment with tactical units in the field. Another prominent program begun during the latter part of 1956 and completed during the latter part of 1957 was the spin test program on the F-102 conducted at the Air Force Flight Test Center. The first step was begun with a series of ground tests on the deployment characteristics of a special spin recovery parachute. A standard F-102A production model underwent modifications for the tests. An artificial wind was created, and when it reached the correct speed, the parachute was deployed. Ground Ground deployments like this provided the necessary data to demonstrate the satisfactory operation of the parachute to be used in the actual spin program. With static ground deployment tests complete, Chief Engineering Test Pilot Dick Johnson was ready to conduct taxi runs with the spin recovery parachute. 5 different taxi runs were made at speeds of 110, 120, and 130 knots. Chute deployment in every case proved satisfactory. The parachute was deployed in flight to determine aircraft response and loads at various speeds and altitudes. Engineers and test pilots alike were satisfied with the results. JATO bottles, a secondary spin recovery device, were also installed on the airplane and were intended to stop spin rotation of the airplane in the event the spin recovery parachute was not sufficient to effect recovery. The JATO bottles were fired to functionally check their operation after they had been exposed to extreme altitude. The JATO bottles were never used or needed for spin recovery. On later spin flights, they were removed from the airplane. This is an animated rendition of the centrifuge at the University of Southern California, on which flight engineers and pilots checked out equipment and pilot reaction prior to actual spins. Here, an engineer went for a spin involving G-forces in excess of those expected in the actual tests. The camera was mounted on the centrifuge itself, and there is no visual sensation of whirling, yet the camera and engineer were revolving at approximately 30 revolutions per minute. As the subject whirled, instruments recorded his reactions. Results of these tests showed exactly how many seconds a pilot can retain control of his faculties at the G-forces expected in the spin tests. Centrifuge rides resulted in modification of the specially designed anti-G suit. Actual spins demonstrated that the plane spun slower and exerted only 1/3 the G-forces expected. Up to this time, there had been no reports of an F-102A indicating a tendency to enter a spin. Most tests were begun from an altitude of 40,000 feet. The airplane carried extensive instrumentation equipment, which was monitored by engineering crews from Convair's San Diego facility. This was the last spin of the program. There were a total of 16 spins conducted for the specification compliance demonstration. In all but 2 flights, recovery was complete in less than 2 turns. Neutralizing the controls was used for recovery in all but 2 flights. In these 2 flights, aileron control was introduced, which would roll the aircraft in the direction of the spin to accelerate recovery. The spin recovery parachute was used only once during the entire test program. This was on the first flight, when the roll oscillations and steep attitude temporarily masked the actual spin from the pilot. Spin characteristics of the TF-102A were determined in 15 spins in 6 different flights. Engineering test pilots William Harse on the F-102A and James Stewart on the TF-102A reported that these aircraft can be entered into a spin and that recovery can be effected in compliance with all military specifications. In-flight load tests were conducted on the F-102A throughout most of 1957. The test program was initiated to demonstrate the structural integrity of wing, fin, and tail of the airplane. Magnetic tapes recorded accurate in-flight test information for direct computer analysis. The recorders registered impulses from pressure transducers on numerous wing and fin cords and airplane responses. This newly developed system accurately measured air loads and dynamic test maneuvers. Up to 300 response functions were recorded simultaneously at individual frequencies on these 14-track recorders. With the recorders and instrumentation installed, the aircraft was ready for flight maneuvers. Symmetrical and asymmetrical test points were selected to produce design loads on fin, wing, and fuselage in a wide range of altitudes and speeds. Measurement of stresses in 360, 180, and bank-to-bank rolls, rudder kick, and roller coaster maneuvers showed that the F-102 air loads agreed closely with design predictions. Test data was also telemetered to ground station to permit flight monitoring. Similar testing proved structural integrity of the TF-102A. At the Convair Analog Computing Center in San Diego, structural load computations were begun. The tape from the recorder in the airplane was played back on this equipment and working copies made. The work tape was then channeled into the central distributing board. The recorded flight information impulses were relayed to discriminators, where signals were separated electronically and transferred to the oscillograph recording unit for data quality study. The separate tracks and frequencies were then fed into the computer. Final solutions were obtained after approximately 5 computer runs. This system cut program time by producing analyzed flight load results in 2 to 4 days. The resultant information was recorded on the direct writing recorder for monitoring and visual record. Results of this test program showed that the F-102A and TF-102A satisfactorily met design criteria. No structural deficiencies were discovered. The program also substantiated similar design techniques employed for the F-106. The structural loads test programs were successfully completed on the F-102A and TF-102A in July of 1957. In mid-August 1957, flight tests were begun by the contractor on the Case 20 conical cambered wing for the F-102A and TF-102A. The new wing, developed jointly by the contractor and the NACA, improves high altitude and low speed flight characteristics of the F-102A. Greater stability and handling ease were evident with the new wing. Lower rate of sink and increased ceiling were also noted. The total efficiency of the F-102 weapon system was increased with this new feature. The Case 20 wing can be distinguished from the earlier design by the pronounced down drooping of the wingtip leading edge and a penetration of the camber further into the wing chord. The Case 10 wing is flattened at the tip and slightly upswept. Case 20 cambering is greatest at the tip, diminishing to zero camber at the wing root. The elevon outer end is approximately parallel with the wing leading edge, and surface area is increased. In cambering the wing, at a given lift, large leading edge pressures act forward on this forward sloping surface, and the total chordwise drag is decreased. Wing tank capacity and center of gravity limits are unchanged. The Case 20 wing was phased into production in June, and phasing in completion was in October 1957. TF Case 20 conversion date was in December. Landing and takeoff handling ease is improved, but distances are the same. The contractor's dynamic measured flight tests were filmed as flight testing continued at the Air Force Flight Test Center. Through September 1957, Convair conducted a downward launching program on the MB-1 rocket. The first ejection firings of the MB-1 rocket were accomplished at the Air Development Center, Holloman Air Force Base, New Mexico. The basic ejection system of the MB-1 rocket consists of 2 ballistically actuated pistons, which eject the rocket from its stowed position in the missile bay to a point well below the aircraft prior to rocket ignition. The principal components of the system are the cartridge chamber, the forward and after ejector guns, the forward and aft auxiliary pistons, the ejection pistons, the rocket retaining latches, and the latch release mechanism, including a rotating breech, and the associated mechanical linkage to effect the latch release. In sequence, the cartridges are fired at the command of the pilot or automatic fire control system. Pressure from these cartridges builds up in the system to the desired level in both the forward and aft ejector guns. At this point, the release mechanism is operated by the forward auxiliary piston force, which in turn rotates the breech, venting excess gases and providing simultaneous latch release. This rotation of the breech also shuts off the flow of additional gas pressure to each gun, preventing cross flow, thereby maintaining pressure at each piston. Relation of forward and aft piston diameters determines the amount of pitch the rocket will assume after ejection. Rocket ignition occurs at a point well below the aircraft, eliminating the problems of heat, blast, smoke, and rocket debris effects on the launching aircraft. With inert drops completed, live firing tests were begun. The MB-1 rocket is an air-to-air weapon capable of containing a nuclear warhead. It weighs about 825 pounds and is 10 feet long with a diameter of 1.5 feet. Rockets were fired after a hot soaking of 120 degrees Fahrenheit for 24 hours. On subsequent firings, the rockets were subjected to a cold soaking at minus 30 degrees Fahrenheit for 24 hours prior to firing. The hot and cold soaking operations were conducted to ensure rocket performance in all environments. After evaluation of data obtained from successful ground firings and inert drops from the airplane, the contractor was ready for live MB-1 ejection firing in the air. The purpose of the aerial firings was to demonstrate the capability of the launching system and to prove the compatibility of the MB-1 rocket with the F-102 airplane. The solid propellant rocket motor develops approximately 35,000 pounds thrust and burns for 2 seconds. Firings were made from altitudes of 20,000 feet to over 50,000 feet at speeds ranging from Mach 0.83 to Mach 1.11 with maximum load factors. Satisfactory and reliable system performance was demonstrated and predicted accuracy obtained. Many new fighter interceptor squadrons were equipped with F-102s during 1957. The performance characteristics of the F-102A on a squadron operations level were reported as very satisfactory, and some squadrons were looking forward to delivery of F-106s in late 1958.